All right, so section 10.3, we're going to basically be talking about arc length and curvature today. Those are the big topics that are in this section. And the idea here is we're trying to find, obviously, we talked about space curves in 10.1 and 10.2. Space curve, as you know, well, that would be kind of odd. Whatever, doing its thing. It doesn't have to be curved, by the way. It could be a straight line. It could be whatever it wanted to be. Okay. In fact, if a feller were to be doing that, let's say you're starting from here and going to here, well, what are you doing? Well, this length right here would be change in x. This length here would be the change in y. That's true. And of course, if x and y were parametric, x and y parametric, and what does that mean? Well, that means that they are functions of t. So in other words, this dx, delta x, wouldn't really be delta x. It'd be dx dt and dy dt, which in other words is saying that would be, f prime of, well, let's back this up a little bit. They'd be derivatives. And derivatives. And so if we start off with an r of t function that is our space curve, and whatever that happens to be, I don't know, cosine of t, t and negative sine of t, just for a good time, for instance, okay? Then r prime of t would be, of course, as we've spoken about, our velocity at any time. This is our velocity function. Cool, that's nice. But what you need to know is that I need to know, how do I find this length? Well, this length here would be the distance formula. It'd be Pythagorean theorem, right? It would be, and because it's a straight line, it would simply be this delta x, delta t, which is again the derivative squared, plus delta y, delta t squared, square rooted, right? And that would be the actual distance from there to there. It'd be great, piece of cake, no problem. And you're like, well, wouldn't it matter how far you travel? Well, how long you travel for? Exactly. And so if this was just you went 5 meters and 2 meters, then it would just be the Pythagorean theorem. But you did it for some amount of time. So what we're going to end up doing is integrating from time equals a to time equals b to find our displacement. And that will always be true, even if it's not a straight line. Because think about this. In essence, if you go from here to here, and then here to here, and then here to here, and then here to there, and then they're the same amount of times in seconds, in essence, you could draw straight lines between them, and you'd be like, oh, let's just add them up. That's right. But by definition, that is literally the definition of an integral, is the idea that you take a whole bunch, an infinite number, of tiny little things and add them together. That's, in essence, what we'll be doing. And so, in 3 dimensions, or in 2 dimensions, but it makes no difference to me, it's going to be the integral of the square root of, okay? And then, so if you use Leibniz notation, so instead of delta x, it's dx dt, dy dt, and dz dt squared. In essence, this is Pythagorean theorem, right? It's a squared plus b squared plus c squared, square rooted, right? And then what is that? So then integrate from a to b. This is arc length. Piece of cake, not a problem. You're like, well, wait a minute. Isn't this the magnitude of r prime? It is. Couldn't I write it like that? You can. Or what are you going to do? You're going to do this to actually do the math. But yeah, it's the same. Good job. Good job. So let's do this one here. Let's do this from 0 to pi. Let's find the arc length from 0 to pi. Cool. Love it. Awesome. So it's going to be the integral from 0 to pi of the squirt of sine squared plus 1 plus cosine squared. It's as if I know what I'm doing. Weird. Sine squared plus cosine squared is 1. So this is actually the square root of 2. Interesting. From 0 to pi. Interesting. And then, of course, if you integrate this, you're going to get root 2t from 0 to pi. So you're going to get root 2 pi is your answer. That's how far it is. Awesome. Can you do it on a calculator? Pretty sure I can. Make sure that you are back in radians before you play this game. Remember, we integrate in radians. We don't take derivatives. We don't do anything calculus-wise ever in degrees. It's always in radians, because radians is actually tied to a distance. So it's F3, integrate the square root of, cool. And so let's do sine of t. Make sure you do this correctly now. Oops. Sine of t squared plus 1 plus cosine of t squared, comma t, comma 0, comma pi. Boom. Boom! Booyah! How fun is that? And of course, if you hit dime and enter there, it'll tell you the exact 4.4. If this was in meters, 4.4 meters is how far you would have traveled. Sweet. Hey, let's do another one. Cool. Let's say you have r of t is equal to 3t plus 5, and then square root of t, and then t cubed minus 5t plus 1, whatever. And I want to know not from 0, moron. 0 is not going to work because t doesn't exist. The middle one doesn't exist at 0. So let's go from 0.1 to 4. Okay, that's hot. So again, you're like, I can do this by hand. You can. Or you could enter this as a function. Okay, and I'm just going to stow that as a, if that's okay with you. Cool. And then what I'm going to do is I'm going to say, all right, uh-oh, what just happened? Is that right? Oh, I did 3t plus 5 is 3. Yeah, no, that's right. No, that's right. It just looks funny. Yeah, that's right. Okay, good. So watch. I'm going to take F3, take the derivative of that with respect to t. Boom. There it is. Now you're like, well, could I simplify this to this all in a computer calculator? Well, you can, sure. So you take the square root of the dot product. Oops, what are you doing, dummy? Hang on, faux. Of that thing with itself. And so I take the square root of that mess. Okay, there it is. And so there it is. And then you're like, oh, that's disgusting. It is disgusting. But remember, what I need to do is I need to integrate that guy from 0.1. Nope, I'm sorry, with respect to t, stupid. From 0.1 to 4. Enter. Fair warning, don't hit diamond enter when you're doing one of these guys. I will tell you right now, it'll speed this process way too long. What a guy can do is go down here to emulator options, and you can unrestrict the speed. Now this little emulator doodad is running at the same speed as my actual processor on this Surface Pro, which sometimes still takes a whale of a time to actually do the job. Oh, why did I pick such a hard one? It's just kind of disturbing. Oh, it's that square root of t. I shouldn't have done that one. No, 55. There you go. 55.26. 55.26. Bam, and you're done. Bob's your uncle. Meters, whatever that's in, you're done. Okay? Notice how it already shut off? That's because when you unrestrict it, it basically thinks that the timer is timed out and it shuts off a lot quicker. Okay? Now, again, that is something I need you to be able to see, though. I need to be able to see the actual work. So you're going from 0.1 to 4 dt, and then, of course, it is the square root of, and that's going to be 3 squared plus 3 1/2 t to the minus 1/2 squared plus, and then it's going to be 3t squared minus 5 squared dt. Now, is that a bugger to integrate? You better believe it. It's a bugger to integrate. That's why it took Betsy a long time to do it. Okay. Notice it gave a common denominator for all of them. That's because this t to the minus 1/2 is in the denominator. And so it just blew that all the way through all of them. That's where that came from. Okay, and again, I'm not going to apologize for giving you ugly when I want you to be able to do them. Okay. Later on, we'll talk about some integrals with some numerical methods. Actually, this is how this one did it. They did it numerically. But I will just say that right now, that if you, and there's a variety of ways to do them, you're certainly welcome to use Wolfram, MATLAB, or any other kind of integral system you want. Knock yourself out. I don't care. But I want to see this part laid out for us. Okay. We'll do one more here. So if R of t is equal to I'm kind of bored of the same ones, but there it is again, whatever. So clearly R prime of t minus 2t is 3 cosine of 3t, and it's negative 3 sine t. Nice. So the integral, and again, let's say we're going from 0 to 4 for our time integral. All right, remember this is our speed. We're doing it over a time period. It's not our speed, it's our velocity over time. So when you integrate over time, you're going to get displacement, of course. That's going to be 4t squared plus 9 cosine squared 3t. This one's going to be ugly. Plus 9 sine of t squared, like so. There's no way I can do that with my hand. There's just absolutely no way. And so that's why I showed a calculator. I mean, there is literally no way that you can do that problem. Okay, the one before, wasn't that nice, Jay? It was awful nice of you to do one where I could use a trig identity. That's cool. You can't do it on this one. It's not going to work. So just be aware. So I'm just going to go, I'm just going to go 4t squared plus, and I'm just going to write that as 3 cosine of 3t, if that's okay with you. Squared, like so. You see that? And then plus, and then I'm just going to do 3. I'm not going to put the negative. I'm just going to go 3 sine, because it doesn't matter. T. Because I'm going to square it anyway. It's going to come to be positive. Anywho, comma t, comma 0, comma 4, I think I said. And this one wasn't as bad because it didn't have that stupid denominator in it, but it's still not good. So again, if you want, just click on it. Emulator options, unrestricted. Boom, 20.56. And that is how far we would have traveled. Again, if that, assuming that was in meters. Okay. And then again, as promised, that's going to shut itself off. Great. Now the next thing we need to talk about is what's called curvature. You're like, what is that, Jay? Is that like a measure of how curved stuff is? Nice job, dude. Nice job. Well, at a point or at a time? Yes. Well, which is it? Yes. Could I give it to you at a point? Yes. Could I give it to you at a time? That's the preferred method. So typically, curvature is going to be a function of t. Okay. Now, there are a couple ways to do it. Okay. Oops, what am I doing? Here's my curve. Here's the tangent to the curve. And so the curvature really is a measure of how far from the tangent the actual curve is. Okay? And so you can write it like this. This is one way of writing it. The books always write this way. And then you're like, why do they tell me that if I'm never going to use it? And that's exactly right. So curvature, let me back this up a little bit. Curvature, just k, is equal to the change in the tangent relative to the arc length, and the idea being, of course, is it's just how far do they bend away from each other, and then of course it's an amount. Okay, it's not positive or negative; it's just an amount. Okay, that's great. Yeah, I get it. So clearly, it's more curved if it looks like this because there's a bigger deviation from it. Less curved here. All right, cool. I buy that. Sure, nice. All right, whatever. Then you're like, well, Okay, well, how are you going to find that, Jay? That's a good question. So there's a couple of formulas. I'm going to show you a couple of them. And if you want to see it on page 709, it kind of works through them. When I first started teaching this, I used to think this was the easiest method of the two. It's not. It is not the easiest of the two. Okay. Now you recall that that t of t is the unit tangent vector. Okay, we found that in the previous section, and so it's the derivative of that, and then of course divided by r prime of t. Okay, and then yes, once again find his magnitudes. Okay, so evaluate it at a particular point in time. This one's not bad. It takes a little bit of work to get there. It takes a little work. Obviously, the top one takes more work than the bottom one does. So my preferred method is this guy. And you do you, but this is the one I prefer to do. And that is, I prefer to take r prime of t cross r double prime of t divided by the cube of r prime of t. This is my favorite way to do it. Now, they're all algebraically equivalent, but that one to me is the easiest of the bunch. Obviously, the curvature is going to change over time. At different points, it's going to be more or less curved, obviously, so it's going to have to change with time. Okay, so just be aware of that. When I get done, this is still going to be a function of time. In other words, it could end up being, it's not, but let's just say it was 3t, right? All right. So when t equals 0, there is no curvature. When 3 equals 1, and it's a curvature of 3, and so on and so forth. Okay, that's how it's going to play out. Okay, so when I do this, let's go do some math. So I got r of t. This is my space curve. My actual curve is going to be 2t, comma, let's do a nice easy one, t squared, comma, sine of t. Awesome. That means, of course, r prime is 2, comma, 4, not 4t, comma, 2t cosine of t. And then, of course, we also need r double prime. And, of course, that's going to be 0 to negative sine of t. Beautiful. Beautiful. Now, it's at this juncture, you're like, well, all right. So, yeah, okay, cool. So, Jay, well, can you... The denominator seems pretty straightforward. I feel like it's just simply the 4 plus 4t squared plus cosine squared of t to the 3/2 power. Remember, just cubed. But you're like, but Jay, remember the square root, or the magnitude simply means you take the square root of this thing here. So it's a squared plus b squared plus c squared square rooted. But the square root is to the 1/2 power. So there you go. So on the top, it's the magnitude of that cross product. You're like, could you do that by hand? I could, but I'm not going to. Okay, so what I'm going to do instead is come in here. I'm going to type in my original function because I feel it's the easiest way to do it. Oh, fiddle faddle. And then I'm going to store that as a. Nice. And then I'm going to take the derivative of a with respect to t. And I'm going to do it again the second time. Nice. Nice. And I think the easiest way to do that on these guys is simply to go stow as, see, what are you doing, jerk? You jerk. So store as, see. So that's my second derivative. And I'm going to store my first derivative back up here somewhere, wherever he went. There, I'm going to store this fella as b. Okay. So what I'm going to do is I'm going to come in here and I'm going to go, all right, second math matrix, vector ops. And I'm going to take the cross product of, now remember, it's r prime, so that's going to be, be careful what you're doing there, Jay. It's going to be b, comma, c. Remember what happens when you cross in the wrong direction, it does what? It makes it negative. Now, is it going to matter in this case? No, because we're going to get this vector. Wait, what just happened here? I feel like, what just happened, man? I feel like something's weird, man. happened? What? Oh. Let's start over, Jay, you moron. So it's 2t. Apparently I put in pluses instead of course, you're all sitting there laughing at me at home. Thanks for help. I appreciate that. Let's try that again. Probably will work this time, moron. Derivative of a with respect to t, and let's stow that as b. There you go, dummy. And then do it again, comma 2, and then store it this time as c. I bet it works this time. What a goofball. All right, so let's try this again. We're just going to go find the cross product. So the cross product of b, comma c. And I got this guy. And you're like, nice. What does that mean? Well, sit tight. So what I need to do then is I need to have this guy such that you're like, okay, so I found the cross product. It's this mess here. It is what it is. You're like, oh, it's gross. It is a little gross. I feel like you're judging, but it is a little gross. So keeping that in mind. But what I really need, I need the magnitude of it. So what I really need, what I really need to do then is simply to go, let's take the square root of the dot product of this thing with itself. Because by definition, that is, that will be the, the numerator there. And you're like, oh, should I write all that down? Yes, I think you should. So it's going to be 2 times the square root of 2t sine t, 2t sine t cosine t, plus t squared sine squared, plus 5. Nice. That thing right there is a curvature. Well, what does that mean, Jay? Well, it means, for instance, if you did this, what would happen if you plugged in 0, for instance? So what would the curvature at 0 be? I don't know. Let's find out. Plug that in. Sine of 0 is 0. This is all 0. That's nice. So is that. So you need 5. On the bottom, you're going to have zeros and zeros. No, cosine of 0 is 1. So you get 1. 1 plus 4 is 5 to the 3/2 power. That's hot. And I feel like this is a square root of 5 and this is a square root of 5, so they're going to cancel out. So you're going to end up with 2 over 5 cubed, which is 2 over 125. That's your curvature, whatever that is, point whatever. Okay. Now you're like, can I finish this on a computer and clean this up a little bit? Yeah, of course you can. So you take this guy here, divide by, and then I could literally do this. I could go, well, for instance, I could take, this bottom guy down here, and I could just type in the way I have it. I did it by hand. Or I could have done it. I could have done it using a computer as well, I suppose, right? Done it using the computer calculations, but I just did this one by hand. To the 1.5 power, right? And you're like, I hit it, and so you get this god-awful formula. It's disgusting, Jay. It is disgusting. So watch what you can do. You can grab this thing, and you can go such that, that's the pipe button right here, t equals 0. Boom. 0.4, which means I screwed something up, is what it means. Did I forget a 2 somewhere or something? Did I forget something? 0.4. So I messed something up, obviously, when I typed it in. So either I typed something in goofy, or I can't do mathematics. One or the other happened. Good question, Jay. Which is it, buddy? Which is it? Oh, it could go either way, to be honest with you. If we're being completely honest, I could have screwed it in. Either one of them I could have screwed up. 0.4. pause if I can figure out my mistake. No, I just suck at arithmetic. No, I suck at arithmetic. It's okay. But I feel bad because I'm an idiot. That's just embarrassing. I really do have a degree. It's from Portland State, but whatever. Let's try that again. Let's do a little math here. Jay can do this. I promise you he can. So, I don't have 5 3 times. I have 5 to the 1/2 3 times. I got a 5 to the 1/2 on top. That canceled out one. Oh, you dummy. It canceled out one of those guys. It left me with 2 of them. And 5 to the 1/2 to the second power is 5. What? Look at that. It's 4.4. Judas Priest. That's embarrassing. Well, yay. If I cared about my embarrassment, I would take the time to edit this. But I hate editing videos. It's the worst thing ever. But honestly, I would do that in class too. I mean, I would just make mistakes, and I think I think it helps you learn. I don't ever do them on purpose because, as a general rule, I make plenty of them, just as a general rule. So I don't need to feel like I need to make more of them ever. That's just weird. Okay. So just be aware of that. So remember, we talked last time about the unit tangent vector. Remember, that is simply whenever I have my space curve doing its thing. At some point, there is at any point in time t. So at t equals some little value of t here, right here somewhere. There is going to be a tangent vector coming off. And of course, that tangent vector is going to be different at different places, obviously, because at different places, the curve's doing different things. Okay? But what it's always going to be, t of t is a unit tangent vector. The idea being is that it's showing the direction that the thing, like if it was a rock, like you had a rock or like a rock tied to a stone, you're spinning it around your head. If the good Lord, that the string broke, if the good Lord shut gravity off today, the planets would just tend to wander off in a tangential fashion. It's the idea of you're just telling me which direction things would go. That's what that unit tangent's all about. Okay? So remember, this guy here is simply equal to r prime of t divided by its magnitude. It's all it is. Nothing to it. Okay? Now you're like, well, that's cool, but I feel like when you're going in a circle, as you well know, let's say we're here, and let's just say we're going around and around in a circle like so. Okay? And let's make the center in the circle, or the center of the circle. How about that? If you're driving around on a racetrack or something like this, going around a circle, what keeps you on the track? Well, friction keeps you on the track. In other words, it's a centripetal force, right? Now, what is that centripetal force being caused by? Is it caused because of an actual rope? Maybe. Is it caused by friction? Maybe. Is it caused by gravity? In the case of us rotating around the sun? Maybe. But what I do know is this. If there is a centripetal force pulling in, it's pulling in like so, always toward the center. But what is the relationship between that and the tangent? These guys are always perpendicular. Always, 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 always. And to find this fella, we want what's called the unit normal vector, or often referred to as just the normal. But I want you to understand it's a unit normal vector. And by definition, the way to find it is simply this. It is this guy divided by its magnitude. That's it. That is the unit normal vector. When I say I want the tangent vector, I want the unit tangent, t of t. Every time, period. People always argue, well, isn't r prime tangent? I said the tangent vector. Thank you. And so I want the unit tangent. When I say I want the normal vector, I want the unit normal vector. Frequently, this guy here, when you first find this guy, frequently, it's the length of it is actually frequently less than 1. And so when you divide by a number, let's say a half, let's say the length is a half, when you divide by its length, you divide by a half, you end up multiplying it by 2. You end up, in other words, you make it up to being 1 unit long instead of making it from being super long down to 1, which is fairly common when you're finding the tangent vector. You divide by a magnitude that's usually bigger than 1 to get down to 1. Frequently, the normal vector will be very tiny, 0.1, 0.2, whatever it happens to be. And so when you divide by that length, you actually make it longer to get up to 1. I'm just saying, just be aware that that will happen. Now you're like, why on earth do I want to know these guys, Jay? It's a fabulous question, sir. The idea is that there's always going to be acceleration, right? When you're going around corners, always. Some of it is tangential acceleration. You're either speeding up or slowing down. That is, you're going to be going this direction, speeding up or slowing down. Okay. but it'll always be in a tangential fashion. And then part of the time there will be centripetal acceleration. Well, that'll be along the normal. That's right. Well, then I'm going to need to have that normal vector to tell me which direction it's headed. That's right. That's right. And then the total acceleration, because these guys are vectors, it'll simply be the vector sum of the tangential acceleration and the centripetal acceleration, which, by the way, is really easy because what are they? They are normal to each other. So it's going to simply be kind of an a squared plus b squared situation. Okay. Now, we're not going, you're like, well, isn't the unit tangent vector 1 and the unit normal vector 1? So the length would be square root of 2. Not so fast, Haas. Those are just giving us the directions. In fact, when you go around a corner that is super duper tight, what kind of centripetal acceleration do you experience here? A lot. And when you're going along here, like, how much centripetal acceleration are you feeling along here? Dude, it's like basically straight, so basically none. That's right. So the only acceleration you get here, and through this standpoint, is if you're speeding up or slowing down, but you wouldn't get any centripetal acceleration because you're not going really around a corner at all. Wait, so you're saying that centripetal acceleration will probably have to do something with the curvature. That's literally what I'm saying to you. That's well done. Exactly right. And so the last thing to say is this, and I'm just going to mention it here, is what's called the binormal vector. Binormal vector. Like binormal, it's normal to two vectors, I guess, if you want to think of it that way. And it is. So binormal vector of t is equal to the cross product of like so. It's important it's in that order because remember, if you change cross products, change the direction. The idea with this has to do with when you're doing torque and you have the right hand rule, okay, for which direction the torque points, which we mentioned I think in section 9.4. Just be aware of that. It's important which one goes first. It's tangent out. Now, good news, we don't do a ton with this guy in our class. So you're like, oh, cool, I got it. Knock it out. Now you're like, are you going to do another example of some of those? No, what I'm going to do is I'm going to move into section 4. So this will be a 10.3 and 10.4 video together because they go together. And the reason the book separates them is because otherwise people will be like, oh, there's too much in one section. Listen, this is what it's all about. I'm going around this corner. I want to know the total acceleration on me. The total G's, if you will, right? Right? So back in the day, I used to take my kids to California for, not my kids, but my physics students. I take them to California every year. We'd go down and we'd ride the roller coasters. We'd measure the G forces. And you remember as you come down, I wish you were here so you could watch me do this. I'm going downhill. Oh! And so gravity is obviously pulling me down. Okay? I go around the corner. I get to the bottom. As soon as I pull up and to the left, there's an X force pushing, going against me, slowing me down the X direction, if that's the forward motion direction, because I'm kind of heading uphill all of a sudden. There's a left and right. There's a left and right acceleration because I'm kind of coming up and to the left around the corner, I guess. And then there's an up and down acceleration because I'm all of a sudden coming back uphill. The total amount of force on me is the vector sum of those three guys, right? And so, but what is it all about? Well, as you go around a corner, there's always going to be this tangential acceleration and there's always going to be this normal acceleration. Okay, this guy here is centripetal. And this guy here will be the tangential piece. And that's the part that we're going to talk about. We're not going to look at them in terms of three axes. We're just going to look at it in terms of, I don't really care. This is just part of a circle, part of an arc, if you will. All right. And so I see a tangent to a curve and I see a normal to a curve. That's all we're going to fool with. Okay. We're not going to worry about which of the three planes they all lie in. Okay. And so when I do this, it's pretty straightforward. You're like, hey, the acceleration, the tangential acceleration, wouldn't that just be, Jay? Wouldn't it have to do with R double prime? Yeah, it sure would have to do with R double prime. What about R double prime? Well, let's think about that for a minute. What is R double prime? Okay. Well, R double prime of t is acceleration. Right? And specifically, that's also v prime, is it not? It's also v prime of t. Nice. And so when I look at this, I'm thinking to myself, oh, that seems straightforward enough. So this is simply going to be equal to v prime, which is r double prime, obviously at some value of t, right? That's what we're talking about, at a particular value of t. Okay, obviously that's true. And then we're going to multiply that by t of t. Okay. Now you're like, well, is this going to be a vector still? No, it's going to be a magnitude, right? Because it's what is the amount of the acceleration. Okay. So when we do this in a few minutes, we're going to take that, we're going to find our double prime, we're going to evaluate it, let's say at 2 or whatever we're talking about time. And you're going to, let's say you're going to get 1, 4, 6 or something. No, that's nice. What is the magnitude of that? So you would find that magnitude. Okay. It's pretty straightforward. It's like, oh, isn't that a lot like you did in physics back in the day? Well, it's a lot like you did in physics back in the day. It's actually exactly like you did back in physics back in the day. And you might recall that centripetal acceleration, I'm going to write that over here, centripetal acceleration. You may remember this from high school stuff, was simply this. So when you do centripetal accelerate, well, let's talk about centripetal. Let's talk about centripetal force. That's mass times any kind of acceleration is going to be mass times velocity, right? So any kind of force is always going to be mass times acceleration, right? Nice, good. And so when we talk about this, obviously, if we're going to find acceleration, we need to find, or if we're going to find force, we need to find acceleration. That's the whole point of doing this. At some point, you're going to want to know, if I know the total g's or the total acceleration, I can find the total force that's acting on this guy, and that's great. But if you remember this from high school, the centripetal acceleration is equal to v squared over r. Right? V squared, what does that mean? Well, it means your velocity squared. Oh, so it's simply going to be v squared, which is a magnitude, obviously. So what you're saying to me, Jay, is you're going to take v of t squared, or if you prefer, r prime of t squared, and you can evaluate it some value. That's right. And then you're going to divide it by the radius. And you're like, wait, divide by the radius? Yes. Leave it there for right now. We'll get to it. Now, it turns out that the curvature is equal to 1 over the radius. Wait a minute. Are you saying that the radius is equal to 1 over the curvature? That's right. Well, that's interesting. That's kind of neato. Look what I have. I have 1 over the radius right here. 1 over radius right here. 1 over radius. Oh. So what you're saying, this is really then just going to be the curvature times this guy squared, and I need a direction, so the direction is simply the normal vector. That's it. That's it. This is all constants. Now, the way your book writes, I mean, I find this just slightly off-putting. The way your book writes it is this. It's v prime, but a small v prime, and then times the tangent vector. The small v prime, not the heavy bolded, and certainly not with a whoosh on top like so. But notice I have them such that it's in... I have it such that I find the magnitude of them, right? The way the book writes it is they write like this, which means you found the magnitude of it. It's not a vector anymore. And then down here, it's simply k times v squared times this guy. Again, these guys are your vectors. They tell you the direction. That's it. That's it. Nothing to it. Let's do one, shall we? Okay. Now, you're like, wait, does this have to do with the planets and all that good stuff? It does. And there's actually a very good read there. It's kind of fun to read through it and kind of see what's what. I'm not going to do one of those right now, but I'm going to do this one here. So let's do... I can't read that. I'm going to pull it up here. I'm going to do one out of the book just because I feel like it. Let's do... Sure. Yeah, that guy right there. So here's my R of t, and it's ti plus t squared j plus 3tk. Now you're like, do you like it that way? I don't. So the first thing I'm going to do is fix it. There, now I feel better. Whew. Doesn't matter, not at all. It just makes me happier. Okay? And since it's all about me, I'm doing it that way, okay? And here we're going to have, of course, 1, 2t, 3. Sweet. And r double prime of t is going to be equal to 0, 2, 0. That's nice. Nice. And so let's start filling in the pieces. Jay, we want to know what happens at t equals 2. I want to know what is the tangential acceleration. I'd like to know what is the centripetal acceleration. A/centripetal. I'd like to know what is the total. Okay. Yeah. Obviously I'm going to add those two together to get the total, obviously. Yeah, I'd like to know a lot of this stuff. I'd like to know how fast it's going. So let's talk about speed. Remember speed, velocity. Speed is the magnitude of it. Right? We talk about a variety of things, but let's just pick t equals 2 because t equals 2 seems interesting. Where am I at t equals 2? Let's start with that one. Well, let's plug that in. Plug it into r of t, and you get 2, 4, 6. That's where you are at t equals 2. Cool. Again, assuming that you start at 0, 0. So that's nice. What is your speed? I don't know. I feel like if I just plug that into this guy, this is also equal to v. It's there. Well, let's put it this way. It's equal to the velocity, but let's hold that thought a minute. So this is going to be equal to, if I plug in a 2 for my t, I'm going to get 1, 4, 3. Nice. Now the speed, or the magnitude of this guy, is simply going to be equal to square root of 26. That's my speed, right? That's my speed right now. And what's my acceleration in terms of my tangent? So when I do this down here, I obviously need to find the magnitude of r double prime, which your book writes as v prime. And so when I do that, it's simply going to be 0 squared plus 2 squared plus 0 squared, which is 2. There it is. And you're like, that seems pretty straightforward. Well, it is pretty straightforward. Okay. So when I start looking at this stuff, I go, all right, the acceleration tangentially speaking is going to be 2 times, now I need my tangent vector. I just don't have it yet. Okay. For my centripetal acceleration, it's going to be messier, but it's going to be my speed squared, right? So it's v squared times the curvature, which again I don't have, but I'm going to go fetch it up in a minute, times the normal vector, which again I don't have yet, but I will find momentarily. Well, momentarily, it's going to be a while. I'm getting there. I promise. I'm getting there. Okay? So let's do this thing. All right? Let's go find t of t. That seems like as good a place to start as anywhere. I got to do them all. So let's just go have some fun with it. So to do that, what I'm going to do is simply take, right? I'm going to take this guy right here, 1, 2t, and 3. And I'm going to divide by the magnitude, which is 1 plus 9 is 10, plus 4t squared. That's it. That's it. See, like, that's t of t. That's right. So then what would t of 2 be? I don't know. Let's find out. It's going to be 1, 4, 3, which we knew already. That doesn't shock me. Over 4, 16, over the square root of 26. You're like, oh, that shouldn't shock me that much either. No, it shouldn't probably. And so 1 over square root of 26, comma, 4 over 26, 3 over 26, and of course you could multiply that through if that makes you happier. And that is your tangential acceleration. Nice. I know that this piece here is 1 unit long, and I know that's 2. So the actual amount of acceleration in that direction is 2 meters per second squared. All right, I just see what it is. Okay. Because how do I know that? Because again, t of t right there, that guy is a 1 unit vector, and I multiplied it by a scalar of 2. That's it. That's it. Nice. Now, I think we should at this point go find this guy, because why not? Okay. So let's take this guy here and let's take the derivative of him. It seems pretty straightforward. So when I do that, I am going to take the derivative, t prime of t. Now, I could do this in my calculator, and I think I will in a minute. Actually, I think I'll do it right now. So let's do this. So it is the derivative of, and you can type it in like this, or you could have already saved it if that makes you happy. Okay, divide by And then it's the square root of 10 plus 4t squared. All right. And then, comma t. There's that god-awful mess. Now, I will tell you right now, don't write that down. Don't write it down. Because what I want out of this, you understand, is I want to know what happens at t equals 2. Does that make sense? That's what I'm interested in. So this is t prime. That's great. But this is the only time I'm going to do that, so I'm just going to grab it. So, boom, there they are. Now I'm going to go ahead and hit enter just for a good time, or a diamond, and get the actual values. And you're like, that's really small. No, it is. Negative 0.06. As promised, most of the time these are going to be tiny vectors. It is way less than a unit long. Yeah, it is way less than a unit long. So what I can do then is this. So you can do it a couple of ways. I mean, how do I want to do it? I guess I'll do this. I'll just demonstrate this way, and then I'll kind of show you how you could actually make it a little bit faster to do what I'm doing here. You divide by 0.24. And then, of course, if you just come in, 0.25, negative, and then 0.625, and then 0.75. Okay, that right there, that is your, that guy right there, because I divided by the magnitude of at 2. This guy right here is my normal vector. Okay, so that's one way to do it. Other way to do it would be to have done this. Come back up here to where it was. That's my vector was right there. Go ahead and hit enter. Bring it down here and then come back into math, matrix. Oh, shoot. What just happened? Math, matrix, vector ops, unit vector, and just make a unit vector out of this guy. And then lo and behold, it's the exact same thing. Okay, there's my normal vector. Now, the hardest part probably of this whole mess is finding the curvature. Probably. Okay, notice that it must be a cross product of the values of t. Some of you are thinking, well, don't I have r prime and r double prime evaluated at 2? Yes, but those are scalars. You can't take cross products of them. So it's at this point where I think maybe it would have been smart. No one's ever accused me of that, being that. What I think would have been smart initially is to come in and actually save this vector. So I'm going to do it. I'm going to do it at this point now. It's after the fact, but I can do it. It's fine. I can still come in here and do it. Goodness sakes. Stow alpha A. Take the derivative of A with respect to t. Let's stow that as B. And then, again, stow that as C. Take the second derivative. Boom. Cool. So what I want to do then is come in here and go second math matrix, vector ops, cross product, right? And I want the cross product of this guy and this guy, which I could have done B and C because I did take the time to save them, but I didn't think about that ahead of time, and I apologize. Okay? So it's negative 6, 0, 2. Now I'm going to go write that down somewhere. So you recall, why is this not scrolling properly? Oh, shoot. You recall that the curvature is r prime of t cross r double prime of t. Find the magnitude, divide by r prime of t, find the magnitude, and then raise it to the third power, right? So when I think about that, I think to myself, well, wait on just a minute. I feel like when I do this problem here, I just found this inside portion. Technically, they're still functions of t. In this case, they're not. In the case of the one I just did, they're no longer functions of t. Okay, are you with me on that? But if they were, what I would do is that normally if that was like, that could be 6t and that could be 2 sine of t or whatever, what I would do is I would take this thing here, and I would take it such that t equals 2, right? Because that's what I'm interested in. And go ahead and enter. Now notice, obviously, in this case, it didn't matter. But in the future, it would matter. So now I would have the values -6, 0, and 2. I want to find the vector. I want to find the magnitude of that guy. So it's going to be 36 plus 4 is 40. And then we already know what the speed is, for heaven's sakes. Up here, we said that the speed was the square root of 26. And we're going to raise that to the third power. So 40 divided by the square root of 26 to the third power. And you get a curvature of 0.3. Okay, remember, what does that mean? It means the radius of the curve is 3.3 meters. Okay, so just be aware of that. I'm not going to ask you about on this particular one, but just be aware of that. So where k is, I'm going to put 0.3 right here. So then my vector then would simply be 26. The square root of 26 squared is 26, obviously. 26 times 0.3. All right. So that is 7.8. That's our scalar. Then it's going to go in this direction. Okay. And then, of course, you can multiply that out. Okay. Jay, could you show us that on the graph? Love to. Come in here to the add a space curve. And recall that our space curve here happens to be, what was it, t, I think? Nope, and you got to use 3 times t, typically anyways. The reason you have to do that is so that it, that's just how that's programmed. I don't know. I blame it on the computer nerds. Okay, there it is. Okay, so I just went 0 to 4. Well, I guess I did. 0 to 4. Whatever, there it is. Okay. And so, yay. Yay. Now, where am I at t equals 2? Well, at t equals 2, we knew that we were at where were we? We were at 2, 4, 6, I believe. Oops. And let's, again, make it somewhat garish so it stands out from the crowd. And then, okay, cool. Now, it's out there. You can't really see it yet. Yes, I can change my window. Let's just do the, oops, oh, don't do 3D mode. Let's do this, dummy. I'm just going to make them all 6. I don't care. And make sure those get chopped off and made into 6s as well. Otherwise, there'll be a problem. And then anyway, if you hit enter, in theory, it changes it so that you can, in theory, see your point, which is not showing up. I'm not really sure what the heck. Oh, I know. I didn't hit enter. There you go. There. Ha! What do you know, Jay? I bet if you hit enter, it'll show up, dummy. Yeah, exactly. Why is that important? Because we're going to put our 2 new vectors on here, and where are they going to start? Well, they're going to start at that point. Are you with me? They're going to start at that point. So here are our vectors. So let's start off with our tangent vector. Well, let's start off with our tangent vector. Yeah, let's go ahead and put our tangent vector in just for fun, shall we? So our tangent vector is, where's our tangent vector? Our tangent vector was at 2 was yes, it was this square root business here. So I'm going to go ahead and just punch that on a calculator if that's all right with you. So I'm going to take b such that t equals 2, right? And then I'm going to divide that by the square root of 26. So I get some decimals going on here, approximations. Does that make sense? Yeah, I'd buy that for a nickel. So 0.19, 0.78. So 0.19, 0.78, and what's the last one? No, where's the last one? 0.588, sure. 0.588. And interesting. And then where do I want to start it from? Well, I want to start it from 246, right? And I'm going to make it, yeah, black's fine. There it is. So that's my tangent vector. Okay, now What kind of tangent vector? Well, it's a unit tangent vector. Okay. Now, I would also like to put in my unit normal vector just for a good time, if that's okay with you. So again, I'm going to start that baby at 2, 4, 6. But this time, and you're like, what? It's pointing off toward Knoyers. No, I know, because that's not the right vector yet. You with me? I just put in where it started from. So our unit normal vector is this guy, right? -1/4. So -0.25, comma 0.625, comma, was it negative or positive 3/4? I can't remember. Oh, don't go to sleep. Don't go to sleep, computer. My other computer's going to sleep. Okay. -3/4. Nice. Close it up. Let's change that color, I guess, because I feel like it. Hit enter. Oh, look at that. Look at that. Hey, they're normal to each other. Hey, they don't look like they're both 1 unit long. Well, they are. And looks are deceiving, and we don't go by looks, obviously. Clearly, here, if you come back to this guy, up here we found our centripetals and our tangential accelerations here. Okay. Again, looks can be deceiving about how curved things are. Okay. So right here, this 7.8 times that business. If I have my calculator here, no, I'm going to take 2 times that guy. 2 times this guy. This will be my tangential acceleration. So notice it's going to be twice as long. I'm not going to type that in, for heaven's sakes. So if I were to type in the tangential acceleration vector, it'd be from here. It would just be going out longer on that black one, twice as long actually. And the centripetal acceleration would be 7.8 times as long as that guy there. And I think, I'm not 100%, but I think you can do this. It's been a while since I tried it. No, it doesn't care for that at all. But you can go back in and multiply it through. And so, let's see. Well, let's see. Well, if you just did 8, what is 8 times 1/4 is 2, right? And then 5/8, this would just be 5, I guess. And that's 3/4, so that'd be like -6. It's like 7.8 times as long, Jay. There you go. All right. And then, of course, the other ones you can multiply by 2 to everybody and see where you ended up. Okay. Pretty straightforward, pretty easy to do. Again, they are perpendicular or orthogonal to one another. Now, I will say this. If someone asked you, hey, what is the total acceleration? You would literally take the magnitude of this vector squared, right? You would take that magnitude of that vector, square it, okay? And then add to the other magnitude squared and then square root it. But you're like, wait, aren't they orthogonal? They are. So all you'd have to do literally is go, wait, this guy is 2 units long. Cool. This guy is 7.8 units long. That's right. And then a squared, b squared is c squared. That's right. So that's the beautiful thing about doing it this way is because they are orthogonal already. All you have to do is play this game at the end. And then, well, that's 8. That's just 8 round the button, really. I mean, 64.84 is 8, right? So 2 to the 0.5 is 8.05. That would be the total acceleration. Okay, and then like, well, what are you saying? Are you saying that when you did that, you would have 2 here and 7.8 here? So then you could actually find the direction where that actual went off towards. You could, sure, but we're not going to. Yeah, you can totally do that. That's it. Nothing to it. Okay, I'm going to pause you for a second, and we're going to do one more example problem here. I'm going to make this one a little uglier, just a little uglier. Okay, just a hair uglier. Not too much, but just a bit more. So R of t is 3 cosine of t. And I'm going to do a couple of cosine, or whatever, 2 t sine t. And again, I'm going to do that so that I don't want anything to go away this time. And then 3t cubed. At this point now, this whole thing is going to be focused on t equals 1. Okay, that's where I want to focus my attention on, and the reason I want to do that is because I want it to be a fairly small number. Okay, but obviously I'm going to have to tell you where we're talking about. Now, would it hurt anything to do it at a different value? No, it should be messier and uglier and bigger numbers. Not going to. One moment. All right, so let's just start working through this thing, huh? So first things first, okay, again, they will have to establish what we're talking about. Cool. So let's talk about where we are. Where are we? At t equal 1. I don't know. That's, again, assuming we started at 0, 0. Well, I don't know. I can't do that in my head because I use cosines and I'm an idiot. So what I'm going to do is go second, and it's not hard. I mean, you're just going to be finding cosines and stuff. Comma 2t times the sine of t, comma 3t cubed. Stow, oops, not alpha yet, sorry. Stow as a. Now what I'm going to do is I'm just going to take that guy and go a such that, oh, what happened? A such that, there you go, t equals 1. So we are, again, make sure you're in radians, 1.62, 1.68. Well, 1.62. That's where we are located. Cool. Okay, how fast are we going? How fast are we going? And what I mean by that, of course, is what is my speed? Cool. Or what is the magnitude of my velocity? I don't know, but I feel like we can do that. So let's take the derivative of a with respect to t. Let's stow that. Gosh, I keep doing that. Let's stow that as b. Cool. And while we're here, let's go ahead and grab b such that t equals 1. So we are traveling at, this is my velocity, mind you, negative 2.5, 2.76, 9. That's great. Okay, that's nice, I guess. It doesn't tell me how fast I'm actually traveling, though, right? So I'm going to go ahead and do it this way. I could just do it Pythagorean theorem in my head, I suppose. That's too much work. I'm just going to take the dot product of it with itself. And I get 9.74. That's our speed. Okay, this is v at 1, of course. Okay, and then you're like, well, all right, cool. Then what's the acceleration? Right? What is the acceleration, or what is v prime, if you will? Because that is something that the computer needs, or the book. You know, we need to know that. So if I do the derivative of a with respect to t twice, I get that mess, and then I simply go such that such that t equals 1, and there's that. Again, I need the magnitude of that, so I'm going to go find the square root of the dot product. Now, again, part of the reason I like doing it with the computer is because that's how it's going to get done, number one. Number two, my problem is that, you know, you've seen me make mistakes. All right? I'm not supposed to be good at this stuff, so I don't know. But also, I could sit in class and do one problem. It would take me literally all night. Step number 4, I made a mistake. The whole rest of it's wrong. The rest of the 47 steps are wrong. I got better things to do with my time, friends. I'm not going to do that. Okay, I'm not going to do it. So when it asks me to find what is the tangential acceleration, what is the centripetal acceleration? Okay, well, the first thing I know is that this guy up here is going to be 18.08. That is the length of it right now. Boom, you're done. That's it. That's all, right? All I need to do now is go find t of t, which I will find momentarily. Okay, and specifically I need to find not t of t. Specifically, I need t of 2 because I'm interested at time equals 2. Okay, and then down here, I know my formula is 9.74 squared times the curvature, which I don't know yet, which I will find momentarily, times the normal function, the normal vector at 2. Okay, so one thing at a time. Let's go knock this thing out. So to find the tangent vector, remember it's simply the tangent vector is simply I'm going to go ahead and write t of t down. So it is b divided by, actually I'm not going to do that. You know what I'm going to do? I'm going to do it this way. Check this out. I'm going to find a unit vector for vector B. And there it is. Okay. Now that's nice, but I'm really interested in t equals 1, of course, right? Oh, I'm sorry. Did I write t equals 2 here? I meant t equals 1. Sorry about that. I just realized that. Sorry about that. So, oops. So, negative 0.26, 0.28, and 0.92. Okay, we know that this is a unit vector. It's 18 units long. Say, that's a lot. It is. It's a bit. It's a bit, if you will. Okay. Now, what do you want to find next? Well, I'm going to find curvature next. No, I'm going to find the normal vector next. Thank you very much. The normal vector, remember, is t prime of t. Let's do that. Okay. Let's go find it. So right up here, I found t prime of t divided by its length, right? I mean, I found that is t of t right there. You with me? I need to find the derivative of it. Okay. So this is the unit vector. This is the unit vector t right there. Okay. So I need to find the derivative of it. So what I'm going to do is take the derivative of this thing with respect to t. I'm not even going to pay attention to what the answer is. I just don't care. Okay? Well, I do, but I don't. Okay? Remember, this is the uglier they get, the funner they are, but the grosser they get. Oh my gosh, it's gross shit. You know it is. I know it is. No, I know it totally is. I'm just going to grab that answer and go such that t equals 1. Oh, come on. It's not that gross of a problem. What the Sam Hill? Oh, wait. Hold up. So there's your answer, and then just give it one of these guys. Boom. Give the approximations. So 0.29, 0.45, and you're like, well, okay, what does that tell me? Well, nothing yet, because right there, that guy is not 1 unit long. How do I know? Because it never is, okay? And again, most of the time, it's considerably shorter than 1. So what you can do is find the unit vector of that thing, and there they go. So 0.5. So 0.5, negative 0.77, and 0.338. Yes, nice. Okay. Now remember, we know this guy is 1 unit long. That's the whole point of making it a unit vector. So what I need to know is I got this number out here, and then I got to find my curvature now. Remember, curvature is always the magnitude of r prime cross r double prime divided by the magnitude of r, right? We already know this bottom guy. We know it's 9.74. I'm sorry, cubed. So we already know that guy. We know that part. We know that part is going to be 9.74 cubed. Boom, done. The top is the part we need to actually figure it out. So we need to go and do this on our calculator here. We need to go cross product. I don't know what just happened, but whatever. Cross product of B, comma, C. Cool. And now we're going to evaluate that at 1, right? We're going to evaluate it at 1. So grab this guy, boom, such that t equals 1. And then we're going to find the magnitude of it. Okay, we're going to find the magnitude of it. So you can do it a couple different ways, I guess. You can do square root of the dot product, which is a pretty easy way to go at this point if you're starting to figure that out. I think it's pretty cool, actually. So dot product of this guy with itself. And you can probably do that You can probably do it just about as fast as doing the square root function in your head, but whatever. And you get 18.69 here on top. Great. So 18.69 divided by 9.74 cubed, 0.02. Nice. Nice. So again, 0.02 times 9.74 squared, you get 1.89. Again, this is the total amount of centripetal acceleration. It's in this direction. This is a unit vector. The total acceleration then would be 18.08 squared plus 1.89 squared. Square root of this would be the total acceleration. Okay? And again, not too difficult. We're going to go ahead and plug that into the computer over here. Just clean all this garbage up. Let's go ahead and put a point in. Let's put a space curve in first, I guess. Our space curve was... What was our space curve this time? I forget. 3 cosine t. So, oh, what just happened? Oh, wait, yeah. Space curve. Three times cosine t. 2t sine t. Now make sure you write 2 times t times sine of t. Nice. And then the last one was 3t, or no, t cubed. Was it 3t cubed or just t cubed? 3t cubed. 3t cubed. Okay. Again, I'm just going to keep it close to 0 since we're just going from 0. We're just going at 1. So there you go. Boom. Up like a bat out of heck. Now let's go ahead and add a point. This is where everything is. This is where we are at t equals 1. We were at, I forget, we wrote it down, 1.62, 1.68. So 1.62, 1.68, and 3. And that's where we are. Okay. And then we can actually talk about, let's go ahead and just put in our acceleration vectors this time, okay? Let's don't put in our normal vectors and our... I'm not going to put in the unit normal and unit tangent vectors, in other words, okay? I know what they are, okay? And I know that my acceleration vector is going to be going in the same blessed direction. So what I'm going to do is I'm going to take and get my calculator out here because, whatever. And I'm just going to go 18 times... So 4.68. Negative. Oh, was it negative? Crap. Was it negative? Shoot, was it negative? It was negative. Now, remind you, if you don't do that, of course, everything's going to go in the wrong direction. But you'll figure it out fairly quickly because you're like, whoa, no. This thing is supposed to be, parallel, all right? I mean, tangential. So just be aware of that. I mean, it should be pretty obvious that it is or it is not. What in the Sam Hill's that crap? Oh, I know what happened. Time. Oh, I know. I pushed the keyboard instead of the actual computer, the calculator keyboard. 5.06. And then comma, and then, shoot, what's the last one? 0.92. 16.36. What is wrong with that, Jay? Well, you didn't start at the right point, you Nimrod. That's what your problem is. You started from 0, 0. You see how stupid that looks? Now, again, I didn't do that on purpose. That's just me not paying attention to what I'm doing. Okay, does that make sense? Now, had I typed in a vector that was the unit tangent vector, it'd only be 1 unit long. Perhaps I will go ahead and do that this time just for fun. Here's my unit. Oops. Oh, shoot. Shoot, darn. Here's my unit tangent vector. Negative 0.26, 0.28. And what was the last one? 0.92. And let's make this something like that. And you can see it's pretty close that the yellow sits on top of the black. Now, obviously, we rounded it. Well, that's not very close. What happened there? Did I drop a negative somewhere? Something happened. Something's not right. Negative 0.26, 0.28, 0.92. Literally, I just didn't hit enter. So when I hit enter, there it goes. Okay, so it makes me feel better about my life. See that little fella's on there? He's a little itty bitty guy. He's 1 unit long. Duh. The black one is 18 units long because that was our scalar for it. Okay, one more. This will be our what do you call it? Our centripetal acceleration vector. And so for this guy, our centripetal will be, I'm just going to go ahead and punch that in real quick if that's all right with you. Somewhere up here. I think I had that actually. I did not have that. I thought I died. I thought I had that, but I did not have that, I guess. Oh yeah, it's right there, dummy. Right there. There it is, right there, yeah. I'm just going to take that guy and I'm going to times it by 1.89. Boom. There it is, 0.95, negative 1.47. Mm, 0.717. And then, I don't know, make it something interesting. Sure. Boom. Look at that, huh? Huh? That hot? Now remember that yellow one, this little fella. Okay, I'm not worried about him. Okay, I mean, we're not worried about him at all. Okay. Now, clearly, if you put this purple one out the top of the black one, I want to finish off with this, and this is what I want to talk about here. Remember, is this. You're going around a corner. Okay? Why do you go around a corner? You've got tangential acceleration, perhaps, pointing you out this direction. But you've got centripetal force pulling you in this way. That's right. Well, why do you go around a corner? Because when you add these vectors, they kind of go like so, don't they? And you're like, what? You mean like, well, it's kind of a poor rendering, but you get the point. In other words, you're actually pulled around a corner because of those two forms. That's how it works. That's literally how it works. That's how you are brought around the corner. Okay? So that should take care of you for sections 10.3 and 10.4. Let me know if you have any questions.